So, now that we have this, we can compute f2. That's what I told you before. So don't be scared by all the algebra on the whiteboard, because there's nothing really scary on it. So we just sum over our stream, and we just, increment or decrement by 1, depending on the hash. Right? And that's what I just showed you. The expectations is all will behave. Now, the next thing that we need to do is we need to get a handle on the variance of this. Okay, so let's just compute the expectation of xij squared. So this was our estimate before, so this is thing raised to the power of 4. And then you can do a lot of index reshuffling. And if you squint at it hard enough, you'll see that this is basically 3 times, that squared sum. Basically, all the odd terms will cancel out anyway, because that means we have at least a singleton Rademacher hash somewhere. And that, of course, makes it go away, so that's very straightforward. And then, well, actually, you would get basically 4 times this for x not equal to x prime, and then we get 1 term corrected, which is exactly what we have. So, it's a little bit of algebra. Does anybody want me to derive that on the whiteboard? No? Okay, good. I appreciate that. So now when we go and compute the variance, well, everybody knows how that works. Okay, I forgot that to be raised to the power of 2, so there's a small typo. You just get this quantity here. Because, well, you basically square that, and then you take away all the diagonal terms, and you can see that this is nothing else than 2f2 squared. So you basically express so this is almost like a self-bounding property. You express the variance through the mean. Right? That's good. Then once you do that, you plug into this average mean theorem, and we're done. Because it tells you then what A and B has to be. Now this expression here, in terms of, tells you how many bits you would need, and that's the statement from the MS paper. Okay, so basically you would recognize some of the terms. The 1 over epsilon squared, that was basically what we needed to boost our accuracy. This log delta was what we got from the Chernoff bound, and then here you get the term that just depends on how many bits you need to actually store the counters and to actually recognize different symbols. Because if I have x many different symbols, I need at least a code that has length log x. So before we go and compute fk in general, I'll give you a short break for 5 minutes or so. Then we'll move on with fk.